Welcome, ladies and gentlemen. May I have your attention, please? Thank you. Let's go ahead and apply the fundamental theorem of calculus part 2. That is, if g is defined by an integral expression, I can take the derivative of that expression, g prime, and it'll undo that integral, with the key difference that now my independent variable will be x inside of my integrand function. And so if I were to find an antiderivative for little f of t, right, call it big F of t, evaluate at my upper limit, it would become big F of x, minus evaluate at the lower limit, big F at a, and then differentiate that, the constant would disappear. So it doesn't matter what that lower limit is, so long as that a is a constant. I know that g of x will be my integrand function, but now with x instead of t. Raise your hand if you had g prime of x equals f of x. That's the fundamental theorem of calculus part 2. Awesome, you guys. Number 2, I can differentiate that integral defined expression, right? I can differentiate that integral defined expression. The key difference is that my integrand function now will have x's in it. And so it's as easy as rewriting 3t cosine of e to the t, except everywhere I see a t, I'm going to have x. It'll be 3x cosine of e to the x. Did it matter that I didn't have a symbolic antiderivative for 3t cosine e to the t? No, I don't have to find an antiderivative. I know that if I could find an antiderivative, evaluate at the upper, evaluate at the lower, right? And then take the derivative of that antiderivative, I get right back where I started. And so the fundamental theorem of calculus, part 2, allows me to skip that step of finding a symbolic antiderivative. So that's powerful. Okay. What questions do you guys have on the first two? Jake?
So when are we supposed to know that we're not supposed to anti-differentiate? Because in 1 and 3, they're asking for the derivative of the given function.
Yes. And the given function.
They are not.
What's that?
And in 2 and 4, they are not. 2 and 4, it says then h, or 1 and 3, it says then g prime of x equals, and then h prime of k equals.
Yep.
So why are we doing the same thing on 2 and 4?
And 1 through 4, you're doing the same thing because finding g prime of g is the same as taking the derivative with respect to x of an integral defined expression, because g was given by the integral defined expression. So every single case we're finding the derivative. It's just written in a different notation. So this one we want to doing a prime for the derivative, this one we're doing d dx. But in each case we're finding the derivative. Does that make sense? So all 1 through 4 are finding derivatives. The derivative of an integral defined expression, and that's why it just says the integrator. Awesome. Let's keep it on. Uh-oh. What's different about number 3? In number 3, my lower limit a will still assume as a constant, but now my upper limit is itself a function of k. And so in this case, I not only have to differentiate the integral defined expression, I also need to multiply by the derivative of the inside function, in this case, the upper limit, m of k. And so here we go. H prime of k will be given by my integrated function with my upper limit in it. So that would be my integrated function evaluated with the upper limit. And then what? Well, then times the derivative of my upper limit. So that would be written as m prime of k. So once again, if I differentiate the integral expression, I'm left with the integrand, evaluate at the upper limit, but then times the derivative of the upper limit in accordance with the chain rule. Raise your hand if you got number 3 right. Did anybody get number 3 right with your... Good. So it's the integrand function evaluate at the upper limit, and then times the derivative of the upper limit. Way to go, you guys. And lastly, the derivative of integral defined expression is the integrand function. Here it looks like our lower limit is not a constant, and so we can rectify that simply by doing a quick rewrite. I'll go ahead and say the derivative with respect to x. And now let's do the opposite of the integral from -3 to 4x to the... Oh no. Rascal rabbit. That's supposed to be a plus. I'm just going to take one step, drag Mr. Prince, take one step, drag Mr. Prince. Hopefully I'll all get there eventually. Okay, so what was the point of that first step? we've gone ahead and rewritten the limits. Now my lower limit is a constant, so I'm all ready to apply the fundamental theorem of calculus part 2, which allows me to differentiate an integral defined expression. When I differentiate this integral defined expression, I'll be left with this integrand function, but now we evaluate at my upper limit, and because my upper limit isn't just the independent variable w, or x, right, or k, it's 4x to the 7th itself a function of x, I need to then multiply by the derivative of that upper limit. So let's go ahead and do number 4 like number 3, but with a specific integrand function. So what do? We'll go ahead and rewrite. We'll go Gaussian. This will become opposite of, and let's go ahead and jump right in my integrand function. I'll rewrite that. 5 plus inverse tangent of w, except I won't have w, what will we have? We'll have my upper limit, 4x to the 7th, right? And then I need to times this quantity. We're going to times that quantity by the derivative of the upper limit. My upper limit was 4x to the 7th, so I'm going to multiply by what? Well, it looks like 28x to the 6th, and that is times quantity. Put it all together, and I better do one more rewrite. Because I want PDF-able, comma, baby, it's going to be negative 28x to the 6th times quantity 5 plus inverse tangent of 4x to the 7th. Let's go ahead and write that. Negative 28x to the 6th times quantity 5. Oh boy. I'm excited about that tangent. That inverse tangent t. There we go. I think we've got it worked out now. So negative came from flipping the limits. Substitute into the integrand function my upper limit. Multiply by the derivative of my upper limit because it was a composite function. Raise your hand if you had number 4 right. There we go, right at number 4. You did. Hey, that's better than the poke in the eye, but it's not, right? It's not everyone. So we want to make sure that we're comfortable applying the fundamental theorem of calculus part 2, which says the derivative of an integral expression is the integrand function itself. They are inverse processes. Whatever one does to a given function, differentiation will get you right back to it. Okay. And does that get us all the way through? It does. So what questions do you guys have about your Bellwork? I wanted to include these then as a follow-up for our practice. So you had an opportunity to get stamps on 4 and 8 of your FTC Part 2 practice worksheet, and it included problems like this on the back side. That is where we use natural log as an antiderivative. So what's a candidate? A candidate for a natural log antiderivative? Well, when we have a quantity on the bottom of a fraction raised to the first power, we know that the power rule would fall short. If I tried to use the power rule to integrate this and find an antiderivative function, I would add 1 to the exponent. My current exponent on that quantity t plus 1 is negative 1 if I were to rewrite that on top. I'd add 1 to the exponent, and my new exponent would be 0, which is no problem. It's just that when I complete my antiderivative power rule and divide by the new exponent, I'd be dividing by 0, and we can't do that. And so the power rule, right, the power rule cannot be employed when I have an overall power of negative 1. That is a quantity on the bottom to the first power. So what are we going to do? No problem. We saw last time that the antiderivative of 1 over x is the natural log of the absolute value of x. It just so happens that this isn't an x on the bottom, it's quantity t plus 1. No problem, I can use the natural log as an antiderivative so long as the derivative of that quantity in red exists. And what's the derivative of t plus 1 with respect to t? Just 1 dt, and so I don't need to provide any constants. We're good to go. I'm already with natural log. I'll grab onto this constant, kick it out front so I don't trip on it. That's just a constant multiplier. It's going to stay around for the party. And rewrite this as negative 3 natural log of absolute value of t plus 1 instead of x, close bars, plus c. That's it. So natural log is an antiderivative rule, right? It's a candidate for an antiderivative rule so long as my quantity on bottom is to the first power. Let's go ahead and box that bad boy and consider the next one. Okay, as I look at this next one, I'm thinking, why is this in with the natural log? Doesn't this look similar to an inverse trig function, right? What inverse trig function does this look similar to?
Tan inverse.
This looks like inverse tangent, almost, right? Except this is not an inverse tangent antiderivative. How come?
Because there's an x in the numerator.
Absolutely. If this had been the integral of 1 over x squared plus 1 with respect to x, it would be straight up inverse tangent of x plus c. That's it. However, we have too many x's. We have too much x, right? Too beaucoup. We have too much x here. So this is not an inverse tangent antiderivative. Instead, if we consider this as a quantity on the bottom, and it is x squared plus 1 quantity to the first power, it's a candidate for natural log, so long as I can provide the derivative of that quantity. Remember, my words for the derivative of natural log of a function is 1 over the function, in this case x squared plus 1, times the derivative of the function. So what's the derivative of that quantity in red? What's the derivative of x squared plus 1 with respect to x? What's the derivative of that x squared plus 1 with respect to x? Sophia? 2x. And so if I had a 2x here, I know exactly where this had come from. It would have come from the natural log of x squared plus 1. Close bars plus c. Right? I know because if I were to differentiate this, I'd get 1 over x squared plus 1, right, times 2x, the derivative of that function. Did I have the 2, though? No, and so I need to account for that by, well, providing a 1/2. Now when I differentiate the natural log of x squared plus 1, right, and then times by the 1/2, I'll get exactly the original integrand function, x over x squared plus 1. And so I must provide that 1/2 to account for the derivative of the base. The derivative of that base, x squared plus 1, is 2x, and I just add the x. That's pretty sweet. What? Why is number 3 in here? Number 3 looks like it has trig rule, trig function written all over it. And well, and why? While the integrand function consists of trig functions, in fact, multiple trig functions, this is a natural log antiderivative. My quantity on the bottom is tangent of m, and that quantity is to the first power. That would be a candidate for a natural log antiderivative, so long as the derivative of that quantity is present. What's the derivative of tangent of m? Secant squared. I don't have to do any provision of a constant or anything. Use substitution, nothing. I'm all ready to go with an antiderivative that's a natural log. This becomes the natural log of absolute value of tangent of m. Close bars plus c. That's it. Awesome. What questions do you have about the first 3? Then let's keep the party going. We can grab onto this constant negative 2/7, and kick it out front where we won't trip on it. And then I'm left with integrating 1 over t with respect to t. That's straight up natural log rule. So long as I remember my constant multiplier, this would just be ln of absolute value of t, close bars plus c. Number middle one on this slide. Why isn't that power rule? Power rule. Power rule, I've got x to the 5th, and the derivative of that x to the 5th would be something like 5x to the 4th. So why can't we use power rule here?
Because you have a constant.
Yeah, that x to the 5th minus 6 is a quantity, making it a quantity on the bottom of a fraction to the first power. If there's something in common I hope that you've seen from these first 5 examples, is that when we have a quantity on the bottom raised to the first power, the power rule falls short as an antiderivative rule. We must use natural log as the candidate. Now, we can only use natural log, though, as an antiderivative if the derivative of the base, that quantity, is present. And right now, most of it is. And so if this had been 5x to the 4th, right, over x to the 5th minus 6, then I know exactly where that would have come from. That would have come from the natural log of absolute value of x to the 5th minus 6, close bars plus c. Why? Because the derivative of this would be 1 over x to the 5th minus 6 times 5x to the 4th. So if I had that 5 there, then this would be my antiderivative function. Did I have the 5 there? No, so what do I do? Well, we've done it time and time again now. We'll provide the 1/5 in my antiderivative to account for the fact that 5 wasn't there. Then if I were to differentiate this function in its entirety, the 5x to the 4th times 1/5, the 5 and 1/5 would cancel out, and I would get my original integrand. That's pretty sweet. I love calculus. No, really, I love calculus. Is number the last one a candidate for natural log? No, how come, Jake?
There's no quantity in the bottom that's raised to the first power.
Absolutely, there's no quantity in the bottom raised to the first power. Even if it had just been m, right, on bottom, m on bottom, right, we could consider as a candidate for natural log, but that m cubed to the third power is never going to be a candidate for natural log unless it was part of a quantity, right? A quantity where the derivative of the bottom existed on top. So can we do u substitution or power rule? Well, what's the derivative of m cubed?
3m squared.
3m squared, and I don't have m squared. In fact, I have a single m. And while I can provide all kinds of constants, right, when I'm integrating or differentiating, I can't provide variables. I can't add an m to that. And so what do? I'll quit, throw it in the gutter, go find another field trip to Wannabowl. No, we're going to stay strong. We're going to buck up. We're going to tighten our belts, and we're going to trudge on. We're going to plow through this. Well, we can use algebra oftentimes, right, to rewrite our original integrand expression in such a way that we can now recognize the rules. And so my quantity is not at the bottom, it's in the top. So I can simply break up the fraction and try again. That's going to be a theme for today's class, as we use logarithmic properties to rewrite an integral, right, an integrand, or set up for a derivative to make the calculus easier. So let's simply rewrite this as break it up. So that becomes m over m cubed minus 1 over m cubed, so I'm breaking up that fraction. It's okay to break up a sum or difference in the numerator of fraction. I just can't break up a sum or difference in the denominator of fraction. Simplify and integrate term by term. So this becomes m over m cubed reduced to 1 over m squared minus 1 over m cubed. And I can integrate term by term just like we differentiate in by term, because now we know that integration and differentiation are inverse processes. And what rule would I use for this first term, 1 over m squared, as an antiderivative? What rule would I use? Power rule. This is m squared on bottom. Don't use natural log. This is a power rule where my current exponent is m to the negative 2. So going term by term, I integrate, add 1 to the exponent. That gets m to the negative 1. Divide by the new exponent is m to the negative 1, right, times negative 1. So I get negative 1 over m as an antiderivative for 1 over m squared. Current exponent on the second term. Current exponent on the second term is m to the negative third. So add 1 to the exponent. M to the negative 2 divided by the new exponent. So m to the negative 2 divided by negative 2. So negative times a negative is a positive. I'm getting plus 1 over 2m squared. And please don't neglect to include a plus c. So we simply used algebra to rewrite our integrand function so that we did recognize what rules we could apply, and then integrated term by term. Evie?
Where did the 2 come from?
Great question. So where did this 2 right here on bottom come from? Right? Where did that 2 on bottom come from?
Derivative, the new derivative,
The
the new exponent.
Yes, divided by the new exponent. So the current exponent right here, I mean, my integrand was m to the negative 3. So I add 1 to the exponent and divide by the new exponent. When I add 1 to negative 3, I get negative 2, and then I divide by the new exponent, I divide by negative 2. Negative divided by negative 2 is positive. So that's why the sign changed too. Does that make sense? Power rule. That's pretty awesome. And so I included these today because we didn't have a chance to, on our early release day, get to any practice together. And I hope that was helpful for you. All right, so we've got lots to check today. We're going to do these separately. So first off, we've got stapler. I'll go ahead and pause the recording now as we go and take care of. Okay, ladies and gentlemen, keep in mind that we will be meeting during final exams week, during an individual exam time. For us, 2A, that's going to be during second block on Thursday, 121. So you must report to regular class time on Thursday, January 21st, and we'll be investigating exponential functions, and we will have an activity that day. You'll also get back your Unit 5 test, so you can see exactly how you did on your Unit 5 test. I'm done with everybody's non-calculator portion, but I'm in the middle of the calculator allowed, and I want to make sure that I have an opportunity to provide partial credit opportunities where they're due, and so the calc allowed particularly is taking a little bit longer. Everyone will get that back on your Thursday 121 class period. Anna?
Do you think that you'll have them in exams before it closes?
Does it close tomorrow or does it close Monday?
It probably closes Monday.
If it closes Monday, then I might have them in, right? If it closes Monday. If it closes tomorrow, then probably not. I'll probably be spending a little bit of my Saturday working on those bad boys. Maybe Sunday. But I do want to get them in so that you can see, and I'll put them in as soon as I finish. And then you get them back to hard copies on that Thursday. Questions about exams week? Okay, then let's go ahead and warm up with our logarithmic properties. Everybody remember your classroom number. So even though we've switched seats and then we switched the desks up for testing formation, we still have the same classroom number this first semester. Everybody remember it, and we're going to go ahead and play a little game. Our game is called the warm-up game. So everybody have your classroom number? I would totally do that if I could do that. So everybody get ready? You might be wondering, what are we getting ready to do? Could it be a derivative, right? A derivative calculation in front of the class? Could it be an integration, now that we're equipped with all our integration techniques? Or could it be something else? I don't know. I'm going to go ahead and program the calculator, though, with a random integer. Awesome. And what are we? Are we 23? 23? 22? Let's do it. Get ready. Don't call out. Oh, gosh, here I was all anxious. What is x squared times x to the fifth fully simplified? Number 7. Sarah says you're correct. So what do we do when we multiply two powers together to have like bases? We can add exponents. That's pretty sweet. Ooh, next one. Get ready. Don't call out. Don't call out. Number 18. Who's number 18? Annika. Annika. Number 3. X to the 10th, survey says. You are correct. So when we take a power and we raise it to a power, what's the shortcut operation with exponents? Multiply. That's going to come back. And lastly, x to the 5th over, not lastly, there's one more. X to the 5th over x squared, that is number 20? X to the 3rd. So when we take a quotient of powers with like bases, we can subtract exponents so long as we do top exponent minus bottom exponent. Yes? Awesome. One to go. So we're going to prove the derivative with respect to x of sine of x is cosine of x. Number 18. Annika! Number 11.
Prove it or just...
Oh, no. Yeah, prove it. Oh, prove it. Well,
I remember you did this. It was crazy.
we don't have time for this yet. This took in a whole class period and then it spilled into the next class period. So we're not going to put Hayden on the spot. This one was a joke, but we are going to prove a couple logarithmic properties. So let's go ahead and take a look now at our note sheet. Think back to our pre-calculus days, well, even our advanced algebra days, right? We could rewrite the log of a product as a sum of individual logs. Where does that come from? Well, if we took two powers and we multiply them together, right? Two powers and we multiply them together, we added the exponents. Recall that our definition of a logarithm is that a logarithm is an exponent, right? A logarithm is an exponent. And so, if we're multiplying our inputs a times b together, then it makes sense that we can rewrite this as the sum of individual logarithms. So natural log of a plus b could be rewritten as what? ln of a plus ln of b, right? We can split up that product inside of my input as a sum of individual logs. We are going to prove that. And so on our note sheet, let's go ahead and let's let x equal ln a, and let's let y equal ln b. Then the invisible base on natural log is what? E. So e to the x equals a. So then e to the x equals a, and e to the y equals b. Why is that true? Well, that's our definition of natural log. So that's true from definition of ln. The pre-calculus definition of ln, I should say. A little joke about day one. All right, so let's go ahead and start with our left-hand side. So ln of a times b is going to equal ln of, what's a?
ln of a plus
was A?
Oh, I,
So A was
either.
e to the x, good, times B, what's B? E to the y, so that was just substitution. We rewrote ln of A times B and we substituted in what A and B equal, so substitution. Would be my justification for that. And we know that when we multiply two powers together with like bases, and right now they both have base E, what is our shortcut operation with the exponents? Right, what can we do with the exponents? Add them together, so we can rewrite this as a single power. What would my single power be? Riley?
E to the x plus y.
Good. E to the x plus y. So what would this be? This would be the product of powers. Product of powers. I wish I was. Oh. Way better. And now I could rewrite the natural log of e to the, right? I could do this two different ways. Remember, we call that a natural log undoes an exponential with base e, or I could grab onto this exponent and bring it down in front in accordance with the log of a power property. Either way, I'm going to get x plus y, right? I'm going to get x plus y here. And that is, again, definition of natural log, we could say, or we could say log of a power, either way. Definition of ln is quicker. And then lastly, but what is x? Ln of A. And what is y? Ln of B. And that's exactly what we wanted. So this was substitution again. And I'm going to put as desired. That's what we wanted to show. We haven't done something like that for a while, but it was sure fun. Don't worry, we get two more chances. Let's go ahead and try another. So, raise your hand if you remember how I could rewrite ln of a to the b, right? How could I rewrite that? Single input. Sophia? Absolutely. We bring down that exponent as a constant multiplier in front. So this equals b times ln of a. Right? This equals b times ln of a. So, dun 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 dun, let's prove it. All right, let's prove it. So what did we do last time? Well, we let x equal ln a. Let's try that again. Let's let x equal ln of a. Then, x equals ln a. Then e to the x equals a. Is that right? E to the x equals a. And that's the definition of ln. Now, ln of a to the b equals, and let's go ahead and rewrite. So we start with our original left-hand side. That was natural log of a to the b. And we'll go ahead and rewrite that. So that is ln of, well, how can I rewrite that? What is a? So a is e to the x. And then to the b. So we're substituting in the green e to the x, right? We're substituting that in for a, and then we still have to raise it to the b power. There's the b power. And there's the b power. What would our justification for this be? Substitution. So substitution is my favorite justification. When in doubt, right? Substitution. Definition of what's your justification for line number 3? Definition of all right, what are we going to do next? Well, we can apply the power of a power property. How can I rewrite e to the x all to the b? Right, this would be e to the what? E to the bx. I can multiply exponents when I raise a power to a power. So this would become ln of e to the bx. And that would be power of a power property. Power of a power property. And ln of e to the bx, again, we could grab my exponent and bring it down in front, but we better not do that. We could do definition of ln and it would be better. We don't want to use our own property to prove our own property. So now we'll do definition of ln, and that's why I chose it last time. Remember, natural log is saying e to the what exponent equals the input, right? A logarithm is an exponent. So what exponent must my base e be raised to equal e to the bx? What? What exponent must e be raised to equal e to the bx? What must be raised to the what? To the bx. That's definition of natural log. That's why we chose that property to use. So we're not using our own properties to prove our properties. Right? We're using other properties to prove our properties. And lastly, you see where this is headed. What would b times x be rewritten as so that we could get to our as desired? Well, b times, and what is ln of a? ln of a is equal to x, so b times ln of a as desired. And what would our justification be for that last line? Substitution, right? Substitution. That's pretty sweet. Feel like you're missing out on the opportunity? Don't feel that way. I knew you would be, so let's go ahead and prove the natural log of a over b is equivalent to, and what is this one equal? Right, what's our goal for this one? How could that be rewritten? Allie?
ln of a minus ln of b.
Great. I'm going to go ahead and pause the recording, and I want you to go ahead and prove that. Okay, you can turn to the nearest person if you like, but you don't need to scoot the desks. We'll come back together and share. Okay, ladies and gentlemen, let's go ahead and take a look at your natural log of a over b is equivalent to natural log of a minus natural log of b proof. Go ahead and raise your hand if you use similar justifications. So do you have the similar line of reasoning? You don't have to use x and y, but yeah, awesome, good. And so we've seen now we can prove these properties. So big whoop, what's the dealio? Well, now we can see how these properties of logarithms make our calculus lives easier. So they're going to help us with calculus on the next. Let's go ahead and take a look at 4 different problems, and we're going to complete them 2 ways. Okay, we're going to complete them 2 ways. The first is old school, using our techniques we've encountered thus far in first semester calculus. And then the second way we complete them will utilize the properties of logarithms, and we're going to see how that it results in an easier path in each case. And so, if I wanted to differentiate f of x and find f prime the old way, that is using the chain rule, I could start out with my chain rule words for the derivative of natural log. So first we'll do a chain rule. Here we go. The derivative of the natural log of a function is 1 over the function times the derivative of the function. In this case, my input function was x to the 7th, so times 7x to the 6th. Well, that's equivalent to 7x to the 6th over x to the 7th, which in turn would reduce to x carry the 9 square root of the inverse tangent 7 over x. That's what you guys are getting, 7 over x? Awesome. Okay, so when applying the chain rule, we see that this isn't too bad, but it would be even shorter, I posit, if we were to apply log properties first. So we just reminded ourselves how log of a power property could be utilized to bring down an exponent in front of my logarithm as a constant multiplier. And so first, let's go ahead and use log props. Let's use log properties. So what can we do to rewrite this? Before doing any calculus, we can keep this as f of x. That is, rewrite it, right, and bring down that exponent as a multiplier in front. So we can rewrite this as 7 times ln of x. That would be the log of a power property. So the log of a power property is equivalent to exponent times the log of the base. Now when I go to differentiate and find f prime, why is this easier than the last? Because my input is not a composite function, right? I don't have to utilize the chain rule. I can now just use the constant multiplier. So this becomes 7 times the derivative of ln x. What's the derivative of ln x? That's just 1 over x. So in the final rewrite, I get f prime equals 7 over x. Was the first way hard? No, it wasn't hard in this case. but it was even easier if we applied our log property first. And that's going to be a common theme for today's class period. If we can utilize our logarithm properties to rewrite our original first, that will result in an easier differentiation. What questions do you guys have on 1? Meg?
Why did you keep the 7 if it doesn't have an x attached to it, if it's just a constant?
Oh, in this case, this is a constant multiplier, right? So we're differentiating 7 ln x. We keep the constant around for the party because that affected the steepness of my original, right? Just like when I differentiate, if I were to differentiate 6x, I get 6. That constant 6 is still there as a multiplier, and then the derivative of x to the first is x. And so that's a constant multiplier. It's going to stay around for the party. The same as if we were integrating, it would still be around for the party as well. Does that make sense? Awesome. Other questions about 1? What then will we do for number 2? Number 2, we're going to trudge ahead, confident in our memorization of the chain rule from first semester. So let's go ahead and apply the chain rule for 2a. Because by golly, we're good at derivative rules, right? We're good because we memorized our words. So the derivative of a natural log of a function is 1 over the function times the derivative of the function. Let's do it. So f prime of x will be given by 1 over the function. In this case, that's x squared secant x, then times the derivative of the function. It just so happens that my derivative of the function is the derivative of x squared secant x, which is itself a product. And so I need to start now with my product words when I take the derivative of the original natural log's input. So what's the derivative of a product of 2 functions? Well, the derivative of a product of 2 functions is the derivative of the first times the second plus the first times the derivative of the second. What's the derivative of secant of x? Secant tangent. So secant x tangent x. So does everybody see our chain rule words? 1 over the function times the derivative of the function. We utilized the product rule when we did the derivative of the function because my original natural log's input was a product. Everybody good? All right, let's go ahead and rewrite that so it looks a little bit better. I'm going to go ahead and 2x secant x. I'm going to group it like that because I think we'll get some reducing here. Over x squared secant x tangent x over x squared secant x. Oh yes, this will reduce nicely. Equals, we can cancel out what, an x and a secant x? So this just give me 2 over x plus, and on the right hand side we have some canceling as well. X squared over x squared, secant x over secant x, and we're left with what? Just tangent x? That's not too bad. So the hardest part here was my chain rule application, but the simplification was okay so long as we remembered how to apply our fraction properties. So what are we going to do differently in B? You guessed it. Let's go ahead and use log properties. That is properties of logarithms to rewrite. So we could go ahead and use log properties to rewrite. What? How could we utilize log properties to rewrite that logarithm? Well, I've got a couple things going on. First, I have a product, right? Don't I have x squared times secant x, a product of 2 functions. The first is x squared, and the second is secant of x. And so we know the log of a product could be rewritten as a sum of individual logs. So in my first step, we're going to do a rewrite, not a differentiation. We're just going to rewrite the original f of x, and we'll go ahead and break it up. This will become natural log of x squared plus natural log of secant of x. Let me see. What other properties could we apply before differentiating? Well, now we have the log of a power. So we could take this 2 and bring it on down in front as a multiplier. So in a second rewrite, again, not differentiating, just rewriting, I can make this 2 ln of x plus ln of secant x. And now I know I can't go any further. We've gone ahead and rewritten everything as a single input and no composite functions exist other than my natural log of secant of x. We won't be able to get rid of that. But we can differentiate now, term by term. So finally, after 2 rewrites, we're ready for f prime. And this will be an easier calculus portion because 2 times ln x will differentiate to 2 times the derivative of ln x. What's that? 1 over x plus, and the natural log of a function differentiates to 1 over the function times the derivative of the function. And secant x differentiates to secant x tangent x. In one rewrite, we get 2 times 1 over x is 2 over x plus secant x tangent x over secant of x. We'll simplify to tangent of x, and we're done. So I want you to look back and go ahead and compare our 2a and our 2b. How do we do? Oh my gosh. Opposite colors too, contrasting colors. Wow, don't blink, you might miss it. That's pretty sweet. So which one was easier? Well, as I look at these, this derivative application of the chain rule was kind of a pain when I had to do the product for the derivative of the inside. This was tricky in that I had to remember my log properties, but it resulted in differentiation that was one step and significantly easier in my opinion. So I would encourage you to always consider utilizing log properties in an original rewrite before then doing the calculus. That is, before doing the differentiation. Let's go ahead and take a look at a third. So in the third one, we're asked to differentiate the natural log of cosine squared x over x cubed. So what are we going to do for the part A? You guessed it, we're going to apply our derivative rules straight up from first semester. So it looks like we've got a composite function. Let's go ahead and apply the chain rule. We know the derivative of a natural log of a function is 1 over the function times the derivative of the function. So let's go ahead and go 1 over the function. That'll be 1 over cosine squared x over x cubed times the derivative of the function. And what rule will we use to differentiate the derivative of that function, that input cosine squared x over x cubed? Yeah, that was a division of subsequent, separate functions of x, so that'll be the quotient rule. Let's go ahead and apply the quotient rule to my logarithmic input. So the derivative of a quotient of two functions is given by the derivative of the numerator, cosine squared, differentiates to power rule, exponent times the base, raised to 1 less, times the derivative of the base. The derivative of cosine x is negative sine of x. So that's the derivative of the numerator times the denominator, as is, that's x cubed, minus the numerator, that's cosine squared of x, times the derivative of the denominator. What's the derivative of the denominator? Well, it'll be 3x squared. All over the denominator squared. So the denominator squared then would be x cubed to the 6th. I'm sorry, x cubed 20 squared would be x to the 6th. So let's go ahead and make sure we have applied our chain rule words correctly. There is 1 over the function times the derivative of the function. And so I've got exponent, derivative of the numerator, times the denominator, minus the numerator, times the derivative of the denominator, all over the denominator squared. So I think we've applied our chain rule correctly. So now what can we do to make this simplified? Well, I think I'll flip that 1 over cosine squared x over x cubed as the reciprocal. That would go to x cubed over cosine squared x, yes? So we'll flip that first one. And we can go ahead and rewrite this again as a single fraction, but now let's go ahead and put this as negative 2x cubed sine x cosine x minus 3x squared cosine squared x all over x to the 6th. Let's take a minute and make sure that we've grouped our signs correctly. So that would be a first term in the fraction, negative 2x cubed sine x cosine x minus 3x squared cosine squared x all over, and we've applied our power x to the 6th. Okay, there's lots of different ways to simplify this. I think we'll get rid of this x to the 6th and x to the cubed right now. would be a good way to do it. So if we get rid of this x cubed, this would become x to the cubed. Good. So let's go ahead and get rid of that right now. And now we can go ahead and put my cosine squared x on the denominator of my fraction and reduce. I think we'll have to do that in 2 steps though. So we would get negative 2x cubed sine x cosine x over x cubed cosine squared x minus 3x squared cosine squared x over x cubed cosine squared x. And then we're one to go. I can see a light at the end of the tunnel, and I hope you can too, because I can't wait for part B. So let's go ahead and finish this out. X cubed over x cubed. Cosine x over cosine squared x. Negative 2 sine of x over cosine of x. And what's sine of x over cosine x? Let's do that. Minus cosine squared x over cosine squared x. And x squared over x cubed. So minus 3 over x. How you feeling, Philly? Okay, so if 1 and 2 were warm-ups, I'm hoping by 3 you're seeing the common theme here. Let's use logarithm properties to rewrite and see if it results in a simpler differentiation. So here we go. 3b. What's our strategy for 3b? Let's use log props. So let's use our logarithmic properties. So I want to find the derivative of the natural log of a function, right? But my function, my input here is, well, a quotient of power. So it looks like we'll get to use a couple logarithmic properties and rewrites, and that's going to make our calculus slides significantly easier. Let's go ahead and see how. So I'll keep the derivative with respect to x because I'm not differentiating right now. What am I doing? I'm rewriting using logarithmic properties. So ln of a quotient becomes natural log of a difference. That is ln of top minus ln of bottom. In our second step, we'll go ahead and utilize the log of a power property in each case. How come? Because this is really a power, cosine of x quantity squared, and this is a power, x cubed. So we'll grab onto my exponents in each case and bring them down in front as a multiplier. Right? We'll bring this down in front as a multiplier. So my second step is a rewrite, not a differentiation, so we still need our operator, derivative with respect to x. How will I rewrite this? Well, ln of cosine of x quantity squared would be the same as 2 ln of cosine of x. Ln of x cubed would be the same as 3 ln of x. And now we're ready to apply our red operator derivative with respect to x. Let's go term by term. So what's the derivative of 2 ln of cosine of x? Well, I'll get my constant multiplier there. Finally, we're doing the differentiation. The natural log of a function will differentiate to 1 over the function times the derivative of the function. What's the derivative of cosine of x? Negative sine of x on top. Good. Minus, going term by term, what's the derivative of 3 times ln of x? Well, that would just be 3 times the derivative of ln x. What's the derivative of ln x?
Over x.
I'm thinking this is way easier. How come? Well, now you guys see it. Negative sine over cosine is negative tangent times 2 is negative 2 tangent of x. Minus 3 times 1 over x is minus 3 over x. Are you guys ready for survey says? Well, it's right on your paper because you got A and B, but I don't. Oh, yeah. Negative 2 tangent x minus 3x. Negative 2 tangent x minus 3 over x. So which one's better? Well, I don't know about you guys, but I'm thinking B was much simpler, yes? So yes, we have to remember our properties, but after rewriting our original using logarithmic properties, the subsequent calculus, that is differentiation, was much easier. that chain rule, in my opinion, was a bear, right? And so was the subsequent simplification. Wasn't that kind of a pain with the fractions? Right. So that's the point of today. Lastly, we'll go ahead and remind you about your change of base properties from pre-calc, and that's going to make your calculus life easier as well. So first we'll do our definition, right? Our definition of logarithm. Our first method, that's the old way, using the chain rule. And then we'll go ahead and now apply our calculus log properties, that is change of base. And so here we go. Y equals log base 5 of x, if and only if 5 to the y equals x. That's the definition, right? That's the definition of a logarithm. So y equals log base 5 of x, if and only if 5 to the y equals x. And now let's go ahead and apply the chain rule. That's our strategy we've been using for all of our part A's, and this one's no different. It's just so when we differentiate, right, when we differentiate both sides with respect to x, then 5 to the y is a composite function. That's why we're going to have to apply the chain rule, because its exponent y is itself a function of x. Let's go ahead and see what that looks like. So on the left-hand side, what's the derivative? The derivative of an exponential function. Well, we memorized our words. We know the derivative of an exponential function is the derivative of the exponent. Well, let's do so the derivative of an exponential function is the exponential function itself times the derivative of the exponent. What's the derivative of y with respect to x?
dy
dx or y prime times the natural log of the base. So for us, that's ln of 5. I better go ahead and, whoa, you guys see that? Pretty sweet. Group it. I'm going to write, actually, the derivative of both sides. This is what we're doing. So the derivative with respect to x of an exponential function, 5 to the y, is the exponential function itself, times the derivative of the exponent, times the natural log of the base, equals, bring down my equal sign, on the right-hand side, meanwhile, back at the hacienda, the derivative with respect to x of x is what? Oh, yeah. Now, what did we want to find? We wanted to find y prime, the derivative of that expression. So what does y prime equal? Let's go ahead and solve for y prime by dividing over the 5 to the y and the ln 5. So y prime is given by 1 over 5 to the y times ln 5. And we're almost there. But what is 5 to the y equal? X. And so my final answer, dy dx, or y prime, is equal to 1 over x ln 5. Woo! Take a break. Had I known, I would have worn my wristband. How could we make that easier? Oh gosh. Well, let's go ahead and use log properties, specifically change of base. So let's go ahead and again use logarithmic properties to rewrite first, and that's going to result in an easier differentiation. So what we call our change of base formula, right? Our change of base formula from advanced algebra and FST and pre-calculus, we could rewrite log base 5 of x as log of input over log of base. In this case, let's use natural log to rewrite this. So let's rewrite this as natural log of big over natural log of base. That is to say, log base 5 of x is equivalent to ln of x over ln of 5. Now let's differentiate. Should we call that? Let's call that change of base. Change of base formula. Now let's differentiate. So if I differentiate both sides, y goes to y prime, and this is a constant multiplier. Isn't this ln of 5 on the bottom, same as 1 over ln of 5 in front? That's just a constant, so I'm going to pull it out front so I don't trip on it, and I'm going to differentiate the natural log of x. What does the natural log of x differentiate to?
1 over x.
1 over x And that looks a lot like our last page, except way shorter. So the derivative of a log with any base, log base b of x, is given by 1 over x, right? And then we're dividing by the natural log of the base. Just like when we took the derivative of exponential, we multiplied by the natural log of the base. So too do we now divide by the natural log of the base if we take the derivative of logarithm. Remember, exponentials and logarithms are inverse of one another, so it makes sense that we're doing an inverse operation now if we're differentiating the inverse category function. That's pretty sweet. So which one is better? This was kind of a pain right there. With the chain rule, that was kind of a pain right there. This one was much easier. So we're going to utilize log properties whenever possible. That's the central theme of the day. All right, let's go ahead and put it all together. So don't call out. Instead, I want you to complete this. So the derivative with respect to x of a natural log of a function. Rewrite with natural logs. So let's apply our change of base to 2. Let's state our derivative, right? Our derivative of a logarithmic function now with any base b, not just a natural log. And then go ahead and identify the overall rule, right? What overall rule could be utilized in each of those three? You don't have to find an antiderivative for them. You can just state what overall rule would be used to find an antiderivative. Okay, you still may be puzzling out which category of function, right? Are we going to use the antiderivative rule for the bottom three? But let's share the top three. So the derivative with respect to x of the natural log of h of x, what would that look like symbolically? Paul?
H prime of x over h of x.
Absolutely. So it would be 1 over the function times the derivative of the function would simplify to h prime of x over h of x. Raise your hand if you had that. That's correct. The derivative of the input over the original input. Good job. How do I rewrite with natural logs? So log base 3 of x can be rewritten with natural logs. What would that look like? Hayden?
Ln of x over
Raise your hand if you had ln x over ln 3. Good, that's our change of base. That's our change of base property, and we can now use that to get a new derivative rule. What's that? At the end of first semester, we're going to add a derivative rule. Yes, now we can handle logarithmic functions with any base b, not just natural log of a function. So the derivative of log base b of x is given by the derivative of this. So 1 over ln of b times 1 over x. We can rewrite that as 1 over x times ln b on the bottom. So 1 over x ln b. Raise your hand if you already had that for number 3. So you already have that for number 3. Good job. Your ln b is on the bottom. That's the only difference. Okay, so what overall rule on the left-hand side? If I wanted to integrate 1 over x squared plus 1, what overall rule are we looking for? Savannah?
Inverse tangent.
Absolutely. That's going to be an inverse tangent of my input. Overall, what rule is the middle one going to be? Right? Overall, what rule is that middle one going to be? Who got the middle one? Overall, Riley?
Natural log.
Yeah, this is a natural log rule. Right? This is a natural log rule, where it's natural log of that function x squared plus 1, but I'd have to include a 1/2. And so this would end up being a 1/2 to account for the derivative of the function x squared plus 1 differentiates to 2x. And so I would need a 2 by a 1/2. So this would be a 1/2 natural log. X squared over x squared plus 1, we haven't done one like this. And so it turns out in order to do this, we would use algebra, right? We'd use algebra to rewrite this. So this would be a use algebra to rewrite. What algebra could we possibly use to rewrite this? Isn't my sum or difference in the denominator? Yes. So we could add a clever 0, would be the quickest way to do it, but you have to remember how to add a clever 0. If I plus 1 minus 1, aren't I adding 0 to that numerator? And yet, in doing so, I would allow you to break up now the sum or difference on top as a sum or difference of individual fractions. Well, my first fraction is x squared plus 1 over x squared plus 1, or just 1, minus 1 over x squared plus 1, and that allows me to utilize inverse tangent for the second half of this. And so if we used algebra by adding a clever 0, that would be a tricky way to do it. The other way to do it would be polynomial long division. When my degree of my numerator is equal to or greater than the degree of the denominator, I can do polynomial long division to rewrite, and then use inverse tangent and power rule. We haven't done that yet. That's pretty sweet though. After the AP exam, we're going to look at some more integration techniques that allow us to handle those kinds of things. What questions do you guys have about our logarithmic properties discussion today? Then, as promised, we've got a little bit of work time. I'm going to go ahead and stop the recording, and you guys can get going on your OTL number 2.